Today I'll be talking about Elastoplastic modeling of sheared colloidal glasses using Eshelby inclusions. This is mainly the work of two students, Sagar Malik and Atharva Pandit, and the simulations, this is a combined study of experiments and simulations on this topic. The simulations were done by Bhaskar and Meenakshi, and we also received valuable input from Peter Shaw at University of Amsterdam. So with this, I would like to start, and the way I'm going to present this talk is I'll try to give an introduction to deformation of glasses, and then I'll try to present the experimental results so that this way we can appreciate the experimental results in a better way. So let me start with an introduction. Yeah, so the problem that I'm going to present today is very simple. You have a elastic solid. You have a solid material. We are going to apply shear stress on this material, and then we're going to see we know what kind of if you plot when we plot the shear stress versus strain, we can understand what kind of macroscopic behavior it has. For very small strains, we see a linear elastic regime. There is non-linearity at larger strains, and there is a yield point beyond which it either fails if it's brittle, or it starts to flow if it is ductile. Okay, so this is a macroscopic description of what happens when you apply stress on a solid. Okay, so be it any kind of solid, this kind of behavior is very universal, and this is what we want to understand. We want to understand this from the perspective by looking at microscopic details. Okay, what I mean by microscopic details is we have these colloidal systems where we can track individual particles, and by tracking these particles in time and also in three-dimensional space, we want to say we want to see what we can say about this problem. Okay, and yeah, so here as we strain this material, the material goes from a solid-like state to a liquid-like state. So that's what is happening here. And why is this problem important? I don't have to really say why this problem is important, because material failure can lead to catastrophes. Some of the examples are shown here, and then the scales are what is really interesting here is the scales are very different. Okay, here this is a geological scale, and then this is a millimeter scale, and both these materials, irrespective of what kind of interactions they have, what is the dimension, what kind of interactions, or the scale, we see something very similar on in materials. Okay, and that is material failure, and this is what we want to understand essentially. That's the larger goal. Okay, but I'm not going to give you the solution to this problem, but we'll pick one small aspect of the problem, then I'll try to address that. Yeah, so these are examples of amorphous solids. Maybe you are familiar by now what amorphous solids are, because there were talks on amorphous solids before in this session. So just to for the sake of completion, I'm going to show this figure. There is a wide, it's a one big umbrella under which there are a variety of materials that can be classified as amorphous solids, starting from metallic glasses to toothpaste foams, and then granular materials. And you can see that the length scale can vary from nanometers to a few centimeters. Okay, so it's a big umbrella under which there are large number of materials that fall, and this is why it is interesting, why we want to understand the failure of these materials. Okay, because there are just too many of them. If you look around, you will see that most of the materials are amorphous rather than crystalline. Okay. Yeah, so this is the problem. So let's say if we have an elastic solid, let's apply stress on it and try to see what happens to it. We know that most crystals are made of dislocations, and when you apply stress on this, the dislocations start moving. That's how plasticity arises in these systems. Okay, this is a very beautiful movie. These are bubble drafts. The experiments were carried out by Bragg and Nye way back in probably 1950s, and this video is taken from Royal Institution Archive on YouTube. And you can see that this is the bubbles are organized in a crystalline in a hexagonal order, and these are examples of crystals, and you can see that when you deform the boundaries, you have these dislocations that run from one boundary to the other boundary. So this is very well understood. Now the question is, can we extend this picture, like these ideas, to glasses or amorphous solids? And the answer is no, because like crystals, the glasses do not have an underlying lattice. Okay, so identifying what is a defect in glasses is going to be difficult, and over the years, like we have come to an understanding, there is a good agreement that what are defects in glasses, okay, and that is there's a localized the plasticity in these materials occur due to localized rearrangement of particles. Okay, so that's the kind of understanding that we have right now, and then whenever you have this rearrangement of particles, it gives rise to long range fields around it, and yeah, so this is what we have. But what we still do not understand is, like how does overall deformation occur due to spatiotemporal correlation of these defects, so what are the spatiotemporal correlations of defects. Okay, so this is where I'm going to shed some light today about the spatiotemporal aspects of defects. How do they organize in space? So yeah, as I said, like yeah, so I'll start with a very basic model, microscopic models of deformation. So I'll present different models. Okay, so these models have evolved over the years, and this is what you will see in the slides also. So we start with Eyring model, which was defined way back in 1936. Let's say there are two states, and these two states are separated by an energy barrier of E, and when we under equilibrium, like the forward rate and the reverse rate are going to be the same. But when you apply external stress on it, like what we are doing is, like we are deforming this energy barrier, and in such a way that the change in one direction is favorable and in the other direction is not favorable, and we can write equations for this and then show that the shear rate, like can be written in this form. So gamma dot is the shear rate, and this is each transformation gives rise to a strain of delta epsilon naught, and these are the forward rate and this is the reverse rate. When you apply a stress, like you are biasing the forward rates and the reverse rates in different ways, and using these two expressions you can come up with a final expression like this. And yeah, omega naught is some attempt frequency, and yeah, the big omega naught is some activation volume. Okay, so this is a very simple picture that was proposed by Eyring, but then this picture was modified by Franz Spaepen, like this was in 1977. One of the important elements that he introduced into this model is the concept of free volume. Okay, so if you have an atom, it can undergo, it can move, it can undergo rearrangement only if there is sufficient volume for it to move. Okay, so he introduced this idea of free volume. So the first term here, it says the fraction of potential sites that undergo a transformation. Okay, so essentially an atom should have sufficient free volume to undergo rearrangement. So that's what it says. This was an important element, and this was very popular for a long time. But however, relation between shear and then free volume has not been successful so far. So this is still a topic of research. And Argon introduced some more elements to this model. He said that when you do a shear transformation, or when you have a rearrangement, there is an increment of elastic strain energy. So one can estimate what is this elastic strain energy from Eshelby argument, and then we can write the shear rate for the system in this fashion. So what is important here is way back in 1970s, they realized that whenever you have a shear transformation or a rearrangement of particles, it is associated with some sort of elastic energy, and this decays in space in some fashion. Okay, so this idea was very much there, during even during 70s. But now, I'm going to introduce some of the models. These are mesoscopic models. One of the model was the soft glassy rheology model that was proposed by Peter Solich, who is sitting in the audience here. So Peter, tell me if I am making any mistake here. So this is your model. Yeah. So according to this model, it's a mesoscopic model. Okay. So there are no particles. So there are small regions, and within this region, this region, mesoscopic regions are associated with a strain variable. Let's say this is L, and This mesoscopic region is associated with some sort of yield threshold. So when the strain in this region exceeds a certain threshold, so the particles rearrange, and that's how they relax. Okay. And there is also elastic energy characterizing the local yield. So which means that each of this zone, like we can think of this this material as some mesoscopic region. So each of this region is associated with some sort of a threshold value for failure. Okay, and from that, one can extract elastic energy characterizing local yield. And the dynamics of the macroscopic state of the system is described by the probability distribution. So this is L, E, and then time. Okay, so they wrote, they proposed an equation of this sort. I mean, this is a very mean field equation. So the first term essentially tells us about the elastic loading between successive yield events. And the second term tells us about yielding of mesoscopic region, and then third one is the relaxation to a new equilibrium. And one of the important so here, what they considered was if you have a region that is flipping, it doesn't affect other regions in the material. So that was kind of a mean field model. Okay. So now, in the recent years, people have started looking at, once again, different kinds of mesoscopic models. Once again, this is not from 2018. These ideas were there from much earlier, very early days. So once again, according to this equation, I mean, this is more relevant to a lattice model. And here, so each lattice point is associated with a yield stress. Okay, so you can apply external stress on this material, and each of these lattice points are associated with a threshold value. And when you exceed that, the local threshold value, it's going to fail. And when it fails, it redistribute the stress, and the stress redistribution is very anisotropic. Okay, so that's what this says. So this is essentially the elastic part, and this is the plastic part. So whenever there is a plastic deformation, it gives rise to this anisotropic stress. Okay, this is how it relaxes. And there are certain, I mean, it's like a toy model. Okay, one can play with, and there are some essentially very simple set of rules. The stress loads locally in the elastic manner while it is below a certain yield stress, and when the local stress overcomes the yield stress, a plastic event occurs. Okay, and whenever you have a plastic event occurring, it redistributes the stress according to this elastic kernel. So that's what it says. And yeah, so I would like to present another example where this is a recent work by Pinaki and his co-workers. What they did was here in this model, they try to when you do this lattice simulations, what you're doing is you're assuming that each lattice site is associated with certain threshold value. Okay, for failure, it could be stress or it could be strain. And usually what you do when you do these simulations is you try to take these yield values from a certain distribution. Okay, so here what they did in this simulation is they did MD simulations, and from the MD simulations they determined the threshold values for failure. Okay, so that was one of the input that they got from the MD simulations, and they also looked at initial stress distribution. So they provided the same stress distribution as initial condition for the lattice models also. So when they did that, what they found is that essentially they could reproduce the stress strain curves that they found in the MD simulations, and also the stress strain curves that they found in the mesoscopic simulations. Okay, so they matched very well. Okay, so this was kind of an overview of what is happening in this field, and when I look at this, I feel very sad. You can ask me why, because this is a theoretician's paradise. Okay, so as an experimentalist, what can I do? So this is what I'm going to tell you in the next few minutes. Okay. Yeah, so the way we set out to address this problem is using colloidal suspensions and advanced imaging techniques like confocal microscopy. So the advantage of using this system is you can get different kinds of phases. For example, crystalline phase, you can also get amorphous phase. And the other advantage is we can look at these particles in 3 dimensions and also follow them in time. Okay, so that's one of the advantages we have working with these systems, and they behave like Hart spheres. So one of the earliest experiments was actually by Argon himself. They use these bubble rafts to understand what happens when you shear amorphous monolayer of bubbles. Okay, but that work did not lead to much progress. Okay, so they just did one experiment and stopped after that. I don't know why, but yeah, in 2007, like Peter Schall and Spaepen and co-workers, they did this experiment where they used colloidal dense colloidal suspensions as models for amorphous systems, and then sheared these materials, and then they could see some very interesting things. So the strain values of these particles are color coded. Positive, red color means deformation in the direction of the applied shear, and blue color indicates in the other direction, in the opposite direction. So this is they found a very heterogeneous strain field, and this is the macroscopic deformation that they had in the system. This is just the displacement of all the particles in the direction of the shear as a function of the distance between the boundaries. Okay, so that's what you have a linear, more or less a linear profile, and they were able to see these kind of rearrangements. So this is at time t is equal to 0, and when you apply stress on the system, you see that a quadrupolar region develops here. Okay, and they showed that it is long ranged. Okay, so everything was done using these kind of pictures. Okay, no yeah, so this was the first step that they took to understand how these systems fail. So now we did several experiments together to understand what is happening in this system. A snapshot of this system is shown here. So these are colloidal fluorescent colloidal particles, and they're essentially suspended in an index matched and a density matched suspension. So these are 1.3 micron particle, 1.3 micrometer in diameter. And yeah, so they are small and slow, so we can follow them in time very nicely. So that's the advantage of using these kind of colloidal systems. So this is a kind of experimental setup that we have developed at ISEP Pune. So what essentially, to perform these kind of shear experiments, what we need is a shear cell, and that can be mounted directly on top of a confocal microscope. And while we shear the system, we can also acquire the images. The shear has to be very slow. So this is the only condition. And this is a cross section of the setup that we have. So one of the boundaries is fixed, the other boundary is moved using a piezo, and the distance between the boundaries is about 40 to 50 particle diameters. The dimensions in the other directions are this is essentially the field of view, which is about 70 particle diameters. The shear rates are very small, and the total strain that we can achieve with this is greater than 100%, and we track a very large number of particles, which is about 250,000 particles.
And the yellow circles are stacked particles?
Yeah, exactly. So that is to prevent crystallization of the boundaries. Yeah.
These are monodisperse.
It's not a biodispersed system. It has 7% polydispersity to prevent crystallization. Yeah. So what we essentially want is we want to look at particle level motion and then try to understand how a glass deforms. And to understand this, what we do is we essentially look at two quantities. One is the affine strain, and then the non-affine displacements on a particle level. Okay. So I will not try to explain this because many of you are familiar with this picture, what is affine and what is non-affine. So if you have any questions, you can ask me later. And essentially this is all done in 3D. So we have a stress tensor of order 2. We pick only this component, which is the component in the plane of the shear, x and z. And what we do is we perform these experiments at a constant shear rate, and in the steady state, this is in the steady state after 50% strain, we take a snapshot of the particles, and what I'm showing here is just a thin slice of particle, but actually the data is 3D. Okay, so once again the particles are color coded. The red color indicates strain in the direction of the applied shear, and then the blue indicates strain in the opposite direction. So you can see there is a network of this blue and red zones. We try to understand this in a bit more detail. To do that, so essentially what you see is there is the strain map is very heterogeneous. okay. So that is the first thing that you notice, and we wanted to understand that picture in a bit more detail. So what we did was we looked at
Just time scales for the capture of the images and the shear rate. So because you're stacking, right?
yeah.
How fast is the?
Yeah, so we are, I mean, the time scales are very, very slow. It's a glass, I mean, in the sense, it's a very dense suspension. The particles don't move much, and also the applied shear rate is very, very small. You know, it's close to quasi-static limit. So the acquiring in that sense is very fast, I would say. Yeah. I mean, that's one of the key things. You know, you need to really go to very slow shear rates to say something meaningful in this system. Otherwise, like, you know, everything gets washed out.
Image the full 3D all the particles?
Yeah. In the field of view, like, you know, that was the field of view. Not everything, but like, you know, within the field of view, like, we had 250,000 particles. So this is the strain correlation. So this is essentially we can decompose. I mean, this is a delta is a vector. We can look at correlations in different planes. Okay, x, y, x, z. So that way, like, you know, we can look at the correlations in different planes. And when we plot the correlations in the x and z plane, you see this nice quadrupolar symmetry. So the strain correlations are very, very anisotropic. And if you, like, you know, project this onto cos 4 theta and take an angular average, then this is what you would get. So it decays with an exponent that is close to 1. And it's a long, where does it decay, okay? So that is, we are not really tested whether it is system size dependent or not, but more or less, like, you know, the point where it decays is the distance between the boundaries in the vertical direction, okay? So this is a kind of,
What is C4?
yeah, so this is, like, you know, we just, okay, sorry. I'll come to that. I'll explain that what that C4 is. It's essentially like we multiply this with cos 4 theta and then take an angular average. If I do an angular average now, everything gets washed out. So we just circular harmonic, like, you know, 4 theta. And so when we look at this picture, it reminds, when we look at this picture, it actually reminds us of something, okay? And that is this problem. You consider an inclusion which is strained within an elastic matrix, and one can solve the continuum equations and try to find out how does the far field strain decay. And this was done by Eshelby in his famous paper, like 1957. If you look at the strain, how does it decay? It decays as 1 over r cube. And if you look at if you look up in the r theta coordinate, this is what you find, a quadrupolar symmetry, which is what we also find in our experiments. But what is interesting here is that the strain correlations do not decay as 1 over r cube, that is predicted by Eshelby, but it decays with an exponent that is, it has a slower decay, okay? So the question here is, why does it decay slowly compared to 1 over r cube? And the answer is because when we determine that strain correlation, we are averaging the strain values over all the particles in the system. So there's not one inclusion, there are many of them interacting with each other. So probably that is the reason why we get this kind of a decay. So that is something that we concluded. But we also did some recent simulations to see like what happens to strain correlations in simulations, the same correlations.
Sorry, so the alpha is positive in your previous.
Yeah. So you can. So this negative sign should not be here. Yeah. Yeah. So we also did simulations and then tried to check how these correlation functions decay in simulations, and it seems to be robust. You know, this 1 over r decay, or like we don't know what the exact exponent is, but it appears to be close to 1. Okay, so it seems to be robust even in simulations, and these are just Leonard-Jones simulations with biodispersed 80-20.
There are many simulations which clearly show that the stress or strain correlation decay are 1 over r to the t or d minus 1.
The way they do the correlations is different, okay? So this here, like what we are doing is we are averaging over all the particles in the system. If I take like a single event, okay, around a single event, it will decay as 1 over r cube.
Okay.
Yeah, it's not like, so so what we did was we thought just to understand like where this exponent is arising from, like we had an idea that there are many inclusions that are interacting with each other. So how do we go ahead with this with this kind of idea, like what we did was we put a threshold on the strain values of the particles. We consider top 10% strain values. And when you look at these top strain particles with top 10% strain, if you look at them in real space, like you will see that they organize in clusters, okay? So they are not distributed everywhere, they organize themselves in clusters. And what we did was we took another case where we identify the particles randomly, okay? We just wanted to see what is the effect of clustering and then random organization of particles. And one can also look at the spatial correlations of inclusions. If you have high strain, when you pick the high strain particles, the correlations are stronger, the spatial correlations are stronger compared to the case where you pick the particles randomly. And I'll just tell you, bear with me for a moment. So what we do is we construct something called synthetic strain field due to the inclusions. We know where the inclusions are sitting. Now we can calculate the strain on other particles, the rest of the particles in the system, using these inclusions, okay? So the strain field due to a single inclusion decays as r cube in 3 dimensions, epsilon cos 4 theta r cube. And the strain on any other particle in the system is going to be a superposition of the strain due to these inclusions. And yeah, so this way we can construct strain fields. And when we do that, this is the kind of picture that we obtain. And this is the strain map that we obtained from experiments. There is no surprise. It's not surprising that since we have picked the high strain particles, there is a lot of similarity between these two. And also when you look at the strain correlations, you see this quadrupolar symmetry. And when you look at these strain correlations, these were the correlations that were obtained from experiments, and these were the strain correlations that were obtained from the synthetic strain fields. They fall on top of each other. What it tells is that if I want to think of a minimal model, all I need to know is if I want to understand why these strain correlations decay with an exponent 1 over r, all that I need to know is where these inclusions are sitting. And that would suffice, it's kind of a minimal model to understand the strain correlations. But we also look at the other case where we pick the particles randomly, the same number of inclusions. The number of inclusions is the same here also. We construct synthetic strain fields, and then if we do the same trick, then we don't get that quadrupolar symmetry. So what it also tells is, yeah.
So are you concluding that the synthetic strain field and the experimental strain fields look the same? Is that what you're saying?
So if I think of a minimal model for explaining why these strain fields decay with an exponent 1 over r, then all I need to know is where these large particles are acting as inclusions. Large strain particles are acting as inclusions, and all I need is information about these large strain particles. Yeah. That's like a minimal model that I can develop.
But in the experimental system, you do see they all seem to be connected through this large strain.
Yeah, so that is not really important. That's what we learn from here, So we can ask these questions in different ways, but when I look at the results, it seems to fall on top of each other. For strain correlations, there could be other quantities where the matching is not good. But at least as far as strain correlations are concerned, we try to, we get a very good match between the experiments and then the inclusion results. And when I
Can I ask something else? I missed, what are you doing about the orientation of the extensional axes of the synthetic exclusions? Are they all in 45 degrees? Or?
Yes. Okay. Yeah, so we can play with that also actually. So that would be the next.
Line.
Yeah. So we did not play with the orientations of those inclusions, yeah. Yeah, so, sorry. When we look at this random distribution of inclusions, we don't get this, which means that it's not only important to know where these inclusions are sitting. There is also the strain. The clustering of these inclusions is also important to understand these correlations. If they don't cluster, probably you don't get this result. Okay, so we need to know how they are correlated in space, also distributed in space. So this is all going back to those mesoscopic models where where they pick only the yield stress as the parameter and then plug it into the lattice model. So one also, one should look at the effect of how these are distributed in space also. Maybe that will give us some new information. So that's the kind of message I wanted to give here. So that was all in the steady state. So what we did was, let's go to let's look at the transient stages of deformation. So what's happening to the correlations in this regime? And so once again, like here we cannot do experiments because experiments we have one or two realizations. If you are in the steady state, then you can do a time average and then get nice results, okay? But if you are in the transient stage, we need several ensembles, and we don't have that in experiments. So what we did was, let's try to see what happens in simulations, okay? In simulations we can get several ensembles. And the first thing that we did was we again put a threshold. This threshold was same as what we introduced in the steady state also. In the steady state, we made sure that the threshold corresponds to top 10% of the particles in the system. So we use the same threshold. And this is the number of inclusions in the system as we strain the system from zero strain, okay? So this is going from 2% strain to 10% strain. You can see that the number of inclusion rises steadily. And if you look at the correlations, strain correlations, this is noisy, but what is we are trying to get more ensembles and smoothen this data, but the trend is very clear, okay? So at very small strains, these correlations decay as 1 over r cube, and then as you go to larger and larger strains, it decays as 1 over r. And if I try to fit an exponent to the tails and then extract an exponent, this is how it seems to vary, okay? It changes continuously from 3 to 1 in the steady state. So now what we did was we also compared, we can also do this inclusion analysis once again. We can identify the particles that correspond to large strain in our system. We can treat them as inclusions. We can construct synthetic strain fields, and then we can compute the correlations for the synthetic strain fields. If we do that, we get nice results even in the transient stages of deformation. So unfortunately, I don't.
So if you start with a bit poorly annealed sample, and then there are a lot of zones which are basically susceptible to this, then you let's say compute the strain correlation. You will expect that the power law will remain 1, right?
See, so far, it's been very robust. We have seen it in experiments, and we have also seen it in simulations.
It looks like that there are these defect zones, and then distribution of this Eshelby these zones are very important.
Yeah, exactly.
To have this 1 over r. Otherwise, if there is only 1, then you
so that's what you see here. So when you are at very small strain values, you have decay that is close to 1 over r cube. Yeah, so they are independent. They are not talking to each other. So as you strain the system more and more, they start clustering and then talking to each other. There is spatial correlation between the inclusions, and that is what is giving rise to a different exponent. And in the steady state, it goes to 1. Yeah, so with this I come to the conclusion of my talk. What I've shown is that plastic deformation in colloidal gases occurs via dynamic formation of these shear transformations. We can say that formation of a high strain zone generates a long range quadrupolar strain field reminiscent of a Eshelby inclusion. The strain correlations in experiments are very well captured by a simple model where we consider the high strain particles as inclusions. And what is really important here is how they are distributed in space. The number of inclusions and how they are distributed in the space. That's what is going to determine how these strain correlations are going to decay. And we have shown that the exponent decays from 3 to 1 when we start from linear regime to go to the steady state. Yeah, with this, I would like to thank you for your attention.
Okay, thanks Vijay for the nice talk. Any further questions?
Yeah, I have one more.
Yeah.
So, have you recently followed this work on this anomalous elasticity, where they talk about, let's say, if you have lot of this
so there where
the renormalization possible, and the decay can, instead of 1 over r cube r to the
Yeah, we are
it
thinking
can be
along
very,
this.
very different.
Yeah, yeah. So the difference between those experiments or simulations and our thing is there, like you are applying a point force kind of thing.
Yeah, yeah.
Okay, and then you are seeing like how if you apply a point force, how does it decay? So
But
I mean.
even there, the argument is that the like a large
There is screening of
density
charges, okay? So which is what we are looking at. I mean, that's one of the surprising thing. Why don't they get screened, okay? Or is it like, are we interpreting these things in a wrong way? So, yeah.
possible.
Yeah.
So you said you could do the correlations in multiple directions, right? So is it 1 over r in every direction? So both shear gradient and shear and vorticity?
I can check that. We have not done that.
So what the direction you were showing now, which one is that?
Is in the plane of the shear.
Okay, but shear or vorticity?
In the plane of shear. So this is, it's not the vorticity direction.
Okay, so
Yeah,
shear.
the shear direction.
I see.
The shear plane.
Yeah. And I have a vague memory that I think Itamar had a paper, right, where he looked at the strain field from a sort of a linear arrangement of these Eshelby.
Yeah, if you have n Eshelbys, like what is the minimum energy configuration for those n inclusions?
Right.
And yeah, it happens to be like they align in the direction of the applied shear. So that's the minimum energy
Do you
configuration.
remember what the strain, how the strain field from that decays?
No, not really.
I have to remember it.
That's not 1 over r cubed, is it? It's something else.
Something else.
Those are quasi-static simulations, and these are finite shear rate simulations.
But I guess that would be.
Yeah, sure.
That you obviously have some sort of correlation between where these guys appear.
Yeah. So once again, like what we are doing here is like it's averaged over like ensembles. So if I think of like beyond E, like you get these shear bands in simulations, and the direction of the shear band is not unique like in different ensembles. It can, the shear bands can be oriented in different directions.
Can you, do you have enough temporal information to sort of say how the appearance of one plastic event biases where
Yeah, this is very difficult to answer in a 3D setting, okay? So one has to go to 2D, and then we are setting up experiments to do these things in 2D.
Okay, cool.
Yeah, yeah. Where we'll have like a finer temporal resolution.
Right.
This number that you said, 250,000 particles in
Yeah.
your field of view, you track all 250,000?
Yeah, so there are some losses, so we tracked all of them. The longer the tracks, the more the particles you lose. So we always look at small windows.
Further questions? Okay, if not, let's thank Vijay.
Thanks.
Okay, so I think this concludes the day.